Okay, question number 40. You are looking at a graph with two values. It is a continuously compounding equation. They give you the equation. I want to explain the variables to you quickly. P of t, and it actually tells you this part in the equation. P of t means that's the amount of money at any given time. So P of t at t equals 3 is 2,000, and P of t at t equals 8 is 5,000. Okay? The part it doesn't tell you is what P sub 0 means. P sub 0 always means this function, which means money, at x equals 0. And that's a given. If you have y sub 0, that means at x equals 0. So P of 0 means this amount at the x. You don't have that either. Okay, in fact, that's what it's asking about. You do have values you could plug in, and that's what we're going to do. So you kind of have it, but I'm going to keep talking about that. Times. E is a number. It's kind of like pi. It's called Euler's number. It's 2.718281828, and it keeps going continuously and forever. Because what this is, that is the exponent base of anything that compounds continuously. Okay, so that's just a number. That's a constant. Don't worry about that. So you actually have that value. R, you don't have R. It never talks about the rate. And unlike linear equations where you can just determine the rate between two points, I can't see the rate here. Okay, or at least not right now. You don't calculate this the same way. And then time, t. Time is the value of t that goes with, let me use a different color because I used that for the time right there. That's this right here, the number of years. Okay, so you do have some time values that match your rate, your P of t, or your balance in the account. So here's what I'm going to show you quickly. You'll notice the only variable that I don't have, and I don't even have a hint of, is R. I can't plug any R's in. For that reason, I am going to go ahead and isolate R right now. And because the rate at the value of 2,000 is the same rate, the same multiplier, I just don't know what it is, at 5,000, and it's also the same rate at 0. I'm going to isolate R in my generic equation. So here's how you do that. P of t, I'm just going to rewrite this equation right here, is equal to P sub 0 e to the RT. The first thing I'm going to do, and you'll notice that R and T are trapped up in the exponents place. So the first thing you do when you see that happen is you isolate the entire exponential part of the expression. So I'm going to divide by P sub 0. Again, I don't know what P sub 0 is, but I'm going to be able to plug numbers in and see if they work. So I know that the y value, or P of t, divided by the original amount is equal to e to the power of RT. Now, the only way to get an exponent out of, or an exponential variable out of the exponent's place, is to do the inverse of the base e. And the inverse of base e is a logarithm known as the natural log. Usually we have like log base 10 or log base 2. And I'll tell you that this is how they work. If I had 2 to the power of x is equal to 64. Okay, you may actually be able to figure that out because you know that 2 times 2 is 4. If you multiply by 2 again, that's 8. If you multiply by 2 again, that's 16. If you multiply by 2 again, that's 32. And if you multiply by 2 again, that is 64. Okay, so I got there by using 1, 2, 3, 4, 5, 6. So that means that x equals 6. So most logarithm or exponential expressions that need to be solved aren't nice even numbers that you can figure out. In fact, a lot of times the x variable up in the exponent's place isn't even a whole number. So the solution to that is to do a log, take a log of both sides. The logs have different bases, and their bases have to match the base of the exponential expression. So I would log base 2 both sides, And some calculators will do log base 2, some won't, but I know the answer. So here's the big deal. Log base 2 of exponent base 2 cancels each other and allows x to drop down just like a regular expression. And then if your calculator will calculate log base 2 of 64, you could just enter that in and you would find out that the answer is 6. Okay? When you have an e, well, let me do you another sample quickly. Another sample of how to solve a logarithmic expression is if I said 10 to what power is equal to 1,000. Okay, you could log base 10 both sides. Okay, now log base 10 of exponent base 10 cancels, so x is equal to log base 10 of 1,000. I want to show you how you would enter that into your calculator if you had a log expression. It's right here. Now let me tell you, you will see log here. This calculator only does log base 10. That's the most calculators are like that, in fact. It only does log base 10, and what this is called natural log. Natural log is log base e, and most calculators do those two and those two only. So I can do log. It doesn't say base 10. You have to know that when you're putting it into your calculator, it is log base 10 of 1,000. And keep in mind, you know that 10 times 10 times 10 is 1,000. If you hit enter, it gives you 3. So you know that x equals 3. Okay? So if I am trying to isolate a variable here, okay, I've got this right here. Keep in mind, I'm just going to plug values in for that, so I'm not worried about that. I'm focused on what I'm trying to isolate, which I told you earlier is r, the only variable you do not have at all. Okay, and the way to do that is to get rid of e. E is the log base e is not called log base e, it's called natural log, and your calculator will do that if you need to put that in the calculator. So you're going to natural log both sides. What that does on the left-hand side is no big deal because you're going to have values for p of t we're going to try, and you're going to have values of p sub o we're going to try, or sub 0. The important thing is what happens on the right-hand side because the natural log of e cancels, and you're just left with rt. Keep reminding yourself, what am I isolating? I'm isolating r. I need r by itself. R, if I divide by t, both sides, the whole thing. Whoop, 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 wrong thing. Here, cancel there. Then I know that r, regardless, and I didn't put numbers in yet, and that's because I want to just make a generic equation. I'm going to put, because the whole thing's over t, I'm going to put 1 over t times the natural log of p of t over p sub 0. Now, this is why this is important, and that is because I have two values, and let me go up here and get them. It's 3, 2,000, 8, 5,000. 3, 2,000. So at year 3, I had $2,000. At year 8, I had $5,000. Okay, I can plug these each in to this expression. So I know that I'm going to do this one in blue. Okay, the rate, I don't know, is equal to 1 over 3 times the natural log of p of t, and keep in mind p of t, and that should have parentheses around it. Keep in mind that p of t is the y value, so it equals to the natural log of p of 2,000 here over, and I'm going to put an x right there because that's what I'm going to try ABCD with. Okay. Furthermore, I know if I do the second point, I know that r is equal to 1 over 8 times the natural log of 5,000 over, and keep in mind the rate's going to be the same, so I can still use x. Okay, so looking at this, if the rate is the same, if these two are the same, then these two are the same. So what I'm looking for is this. I'm going to put 1/3 natural log of 2,000 over x and 1/8 natural log of 5,000 over x. I'm going to put them both into the calculator as separate values. So I'm going here. I'm going to put a new equation, and I'm going to type in, and my screen's going to shift because I'm flipping out my keyboard here. Okay. Zooming back in on where I was. All right, right there. Okay. So one of my equations, I'm going to say that y of x equals, open parenthesis, 1/3 times the natural log of, I didn't type that right, 1/3 times the natural log of 2,000 divided by x. Okay, so that's my red equation. Okay, you'll notice it says missing right delimiter. Do you see that I've opened a parenthesis for natural log, opened what was inside natural log, forgot to close it. So that means that I just need to put in another parenthesis right there. Okay, now I'm going to do a different one. I'm going to do the other equation. Okay, and that equals to 1/8 times the natural log of 5,000 divided by x. And I'm going to make that be a different color. Make that one blue. Okay, checking 1/3 natural log of 2,000 over x, 1/8 natural log of 5,000 over x. I'm going to go to the table here. Okay. And what I'm going to look for, notice that the table, it always starts out with crazy numbers. All right, so here's the thing. What you're going to do is just tell it to start at each value of that we're trying. So I want to know, is the rate the same if you started out with 540? Oops. All right, backspace. 540. I want you to remember that it will not let you hit enter here. You have to actually hop over there for it to go to 540. All right, if these two equations were the same, they would have the same rate. Okay, and they don't. Those rates are vastly different. That's almost 44% for the first equation versus around 28 for the second. 540 is not your answer. I'm going to do 1,000 and look at, and keep in mind, you don't hit done, you tap over. This first at 1,000, the rates are for Y1, it's 23%, and for Y2, it's 20%. If 1,000 was the starting amount, they should have the same rate. And then I'm going to try 1160 and hop over here. Okay, at 1160, the rate for the first one was about 18%, and the rate for the second one was about 18%. That's super close. I want to check and make sure the last one isn't closer. So 1270, I have to hop over here. At 1270, it's 15 versus 17. So the third one, and again, take a look at it, 1160. At 1160, the rates are real close, and keep in mind that E and natural log, those are irrational numbers, so you might get decimal differences, but it's so close, that's it. The rate was about 18%, and so the answer is C. You had to have started with $1,160.